Covalent bonding is the sharing of electrons by two elements, and it is formed by by overlapping of orbitals. With respect to sharing of electrons, there are three types of covalent bonds. Those are single covalent bond, double covalent bond, and triple covalent bond. In a single covalent bond, there is one electron shared by each element, and then two and double, and so on. With respect to orbital overlapping, there are two types of covalent bonds that are sigma bond and pi bond. First is the sigma bond. Sigma bond is represented by this sign. It is formed through head-to-head or head-on overlapping of orbitals. And it is a very strong bond. Now, there are three different types of sigma bonds, which are SS head-to-head overlapping, SP head-to-head overlapping, and PP head-to-head overlapping. So what is SS head-to-head overlapping? For example, in the hydrogen molecule, we have two hydrogen atoms. Hydrogen's configuration is 1s1. So this means that hydrogen has only one s orbital and one electron in that 1s orbital. So when two hydrogen atoms combine, this electron is shared. And because there are two s orbitals, so it is called SS head-to-head overlapping. So for example, this is the this is the orbital of the first hydrogen, and this is the orbital of the second hydrogen. So hydrogen will have this overlapping between the s orbitals. And this is the region where the electrons are present, where the bond is formed. While these are the nuclei. So now each nucleus pulls on the two shared electrons, and that is why the atoms are held together. This can also be represented as a molecular orbital. That is when s and s orbitals combine. This is the molecular orbitals structure. Next is SP head-to-head overlapping. Over here, we'll take the example of hydrogen fluoride. Hydrogen's configuration was 1s1, and fluorine's configuration is 1s2, 2s2, and there are 9 electrons. So 1, 2, 3, 4, 5. So we have now total 9 electrons. Now we can see over here that fluorine's empty shell, empty orbital, is a p orbital, and that is the pz orbital. So for hydrogen, there will be an s orbital, while for fluorine, there will be a p orbital, and the shape of a p orbital is lobe shape. Now, when these overlap, they will form the sp head-to-head, and that is represented in this way. This is the nucleus of hydrogen, and this is the nucleus of fluorine. And the molecular orbital for the sp head-to-head is somewhat like this. Third is the PP head-to-head overlapping. Over here, we'll take an example of fluorine molecule. It has two fluorine atoms. Fluorine's configuration, as we did in the last slide, is 1s2, 2s2, and 2p5. So again, over here, we can see that the empty orbital in fluorine is the pz orbital. So two p orbitals will be combining. P orbitals are represented by a lobe shape. So when they combine together, these are the two nucleus, and this is the structure for the PP head-to-head. And if we draw the molecular orbital for this, the structure is this is the molecular orbital with the nuclei over here. So what we understood over here was that covalent bonds are formed by the sharing of electron, and that happens when orbitals overlap. So covalent bonds can be of three types. So those are single, double, and triple covalent bonds. Also, according to orbital overlapping, there can be two types of covalent bonds, sigma bond and pi bond. There are three types of sigma bonds. The first is SS head-to-head overlap. In SS head-to-head overlapping, we took the example of hydrogen. Hydrogen has one s orbital. So in the hydrogen molecule formation, two s orbital combine, and s orbitals are spherical in shape. So this is the formation of SS head-to-head, and this is the molecular orbital. Then SP head-to-head overlapping, we took the example of hydrogen fluoride. Hydrogen has one s orbital, which has one electron, and fluorine has one pz orbital, which is incomplete. So that pz orbital, this is the pz orbital, the pz orbital and the pz orbital and the s orbital of hydrogen will combine to form sp head-to-head. And this is the molecular orbital shape for the sp or head-to-head. Next is the PP head-to-head overlapping. Over here, we took the example of fluorine molecule. Fluorine has one pz orbital, which is incomplete. So two pz orbitals combine together. P orbitals have the shape of are lobe shape. So when they combine, this is the structure of a PP head-to-head, and the molecular orbital for the PP head-to-head is in this shape. Now, next is pi bond, the second type of covalent bond. Pi bond is represented by pi, and it is formed through side-wise overlapping of p orbitals. It is always formed through p orbitals. So, for example, if this is one p orbital, and this is the second p, and this is the second p orbital. So this is how they'll form the pi bond. And what's important to note over here is that the pi bond is much weaker than the sigma bond. Now, when are sigma bonds formed and when are pi bonds formed? So if the molecule has, if the bond is a single covalent bond, then there is one sigma bond. If the bond is a double covalent bond, then there is one sigma bond and one pi bond. And if the bond is a triple covalent bond, then there is one sigma bond and two pi bonds. We'll do the structure and how to draw the pi bond sigma bonds in more detail in hybridization. For example, if we have ethanol, that is CH3COOH, and we have to determine the number of sigma bonds and the number of pi bonds in ethanol. So the number of sigma bonds are all single bonds. So over here in CH3, there are three hydrogen atoms. So there will be three single bonds over here. If we do the complete structure, it would be there are three single bonds here. 1, 2, 3, 4, 5, 1 in between these two, 6, and then 1 here we have a double bond, so 1 will be a sigma bond, 1 will be a pi bond. So 1, 2, 3, 4, 5, 6, 7. 7 of these are sigma bonds, and this is the pi bond. Next are the dot and cross diagrams for covalent molecules. First is ammonia, NH3. First, we have to determine which element will be the central atom. The central atom is the element which has the maximum capacity of forming bonds. So over here, nitrogen forms 3 bonds and hydrogen forms 1 bond. So nitrogen will be the central atom. Now, nitrogen has 5 electrons in its outer shell. So we'll draw those 5 electrons. This 1, 2, 3, 4, 5. We'll place 3 hydrogen in this manner. Hydrogen has 1 electron. So for that 1 electron, we'll use a dot. This is the structure for ammonia. For SiCl4, that is silicon tetrachloride, silicon forms 4 bonds, chlorine forms 1 bond, so silicon is the central atom. Silicon has 4 electrons in its valence shell. So 1, 2, 3, 4, and then we'll place the 4 chlorines. Chlorine has 7 electrons in its valence shell. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. This is the structure for SiCl4. Next is H2O2, that is hydrogen peroxide. Over here, oxygen can form 2 bonds and hydrogen forms 1 bond. So oxygen will be the central atom. There will be 2 oxygen atoms and there will be 2 hydrogen atoms. Oxygen has 6 electrons in its valence shell. Hydrogen has 1 electron in its valence shell. This will be the structure for H2O2. Now nitrogen Nitrogen forms 3 bonds. And nitrogen has 5 electrons in its valence shell. So nitrogen will form a triple covalent bond. So over here, one will be a sigma bond and two will be pi bonds. But in the dot and cross diagrams, we do not show sigma bonds and pi bonds separately. We just show them by dots and crosses. Next is PCl5. Phosphorus has the configuration 1s2. Phosphorus has 15 electrons. Atomic number is 15. So this is the configuration for phosphorus, and chlorine we know forms one bond. Now over here we have phosphorus as a central atom, obviously, because it forms more bonds. But what the problem over here is that phosphorus has 5 electrons, but if it forms 5 bonds, then there will be 10 electrons in its valence shell. So this goes against the octet rule, but it is possible because in phosphorus, the valence shell is the third shell. This is the third shell. And the third shell has a 3D orbital as well. So for phosphorus, we will draw the 3D orbital. And when energy is provided over here, this electron moves to this orbital. So this will be the configuration of phosphorus in the excited state. The earlier one was the ground state, and this is the excited state. Now it has 5 incomplete orbitals. So that's why it can form 5 bonds. So this will be the structure for PCl5. Again, doing this again, the phosphorus configuration was 1s2, 2s2, 2p6, 3s2, and 3p3. So since its valence shell was the third shell, there is also an available 3D orbital, 3D subshell. Therefore, when phosphorus goes into its excited state, one electron from the 3s2 orbital goes to the first 3D orbital. So now it has 5 orbitals with 5 incomplete orbitals, and which is why it can form 5 bonds. This is termed as octet expansion. and it is an exception to the octet rule. Next is SO3, sulfur trioxide. In sulfur trioxide, again, sulfur will be the central atom because it can form more bonds. Now, this is a bit contradictory because both sulfur and oxygen are in the same period, so in the same group, sorry. So they both form 2 bonds conventionally, but in sulfur again, the octet expansion is possible. Sulfur's configuration would be so again in sulfur, the outermost shell, the valence shell is the third shell. So a 3D subshell is also present. So we'll draw the 3D subshell. And over here in the excited state, this electron is transferred over here. This electron is transferred over here. So now there are 6 orbitals with 6 incomplete orbitals. So sulfur can form 6 bonds. These are the 6 electrons in sulfur's valence shell. And then for oxygen, there are 6 electrons in oxygen's valence shell. So this will be the dot and cross diagram for sulfur trioxide. However, for example, phosphorus is from group 15, and instead of phosphorus, there was nitrogen. So nitrogen's configuration is 1s2, 2s2, and so this is the configuration for nitrogen. However, if we had to form NCl5, this would not be possible because nitrogen's valence shell is the second shell and there is no 2D subshell available. So I'll draw this more clearly. So nitrogen can only have 3 incomplete orbitals. So it can only form 3 bonds because it cannot have an excited state. This electron cannot go to another orbital. However, in phosphorus, this is the configuration for phosphorus, and as its outermost valence shell is the third shell, so it has a 3D subshell available, even though it's empty. So in the excited state, this electron can move over here, and then it will have 5 incomplete orbitals, so it can form 5 bonds. So that is why in phosphorus, in PCl5 and SO3, there are a total of 10 electrons in the valence shell. And in sulfur dioxide, there are 12 electrons. Hybridization occurs when different energy atomic orbitals combine together to form equal energy orbitals at intermediate energy levels. So those orbitals are called hybrid orbitals. Now in our syllabus, there are 3 types of hybridizations. Those are SP3, SP2, and SP. For SP3, we'll take the example of methane, or in fact, ethane. So carbons, first we'll write carbons configuration, and I'm writing this configuration in the vertical form. E represents energy. Carbon has 6 electrons. So this is carbon's configuration for the ground state. Now, first, when carbon goes into the excited state, this electron goes into the pz orbital. So this will be the configuration for the excited state of carbon. Now in sp3 hybridization, what happens is these 4 orbitals, they combine together to form a hybrid orbital at an intermediate energy level. So after hybridization, if we write a carbon's configuration, we'll have the 1s orbital here, and then we'll have 3 orbitals and these are called sp3 hybrid orbitals, and these are at an equal energy level, which is between the energy levels of 2s and 2p. Now when we have carbon over here, we have another carbon over here, and then we have 3 hydrogens. So carbon will now form, each carbon will now form 4 bonds because it has 4 incomplete orbitals. I'm drawing half of the orbitals. These are the sp3 hybrids. They have another lobe below opposite to it, but I'm just drawing one of them. Over here we have hydrogen, 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 Hydrogen has only an s orbital, so that is spherical in shape. So for hydrogen, we'll draw the spherical orbitals. So this is the structure for C2H6, that is ethane. Once again, what happened was that in carbon's ground state, from carbon's ground state, we move to carbon's excited state, that is one electron from the 2s subshell move to the 2p subshell. And after that, what happened was that these four orbitals, they hybridized and formed SP3 hybrid orbitals, which are at an intermediate energy level 2, where that is between 2s and 2p. Now carbon can form 4 bonds. Those are drawn in red, one with each carbon and then one between the two carbon, one with each hydrogen and one between the two carbons. And then hydrogen has only an s orbital, so that is spherical in shape. So this is how we'll draw C2H6. And the red orbitals are the sp3 hybrids. Next is the SP2 hybridization. Now in SP2 hybridization, I'll take the example of C2H4. So again, we have carbon. Its configuration is somewhat like this in the vertical manner. This is for the ground state. In the excited state, this electron moves over here. So this is the excited state. Now in sp2 hybridization, one s orbital and two p orbitals combine to form the sp2 hybrids. So for example, these three orbitals will combine and form an energy level at an intermediate energy. They will form an intermediate energy level between 2s and 2p. So now we can write the configuration as this is 1s, this is sp2, and this is 2p. Now these three electrons that are at the same energy level will form 3 sigma bonds, while this fourth electron will form a pi bond. So we'll have 2 carbons. I'm drawing the sp2 hybrids in red. There are 3 sp2 hybrids. And the fourth is the 2p orbital. Now the 2p orbital will form a pi bond. We learned earlier that pi bonds are formed by sidewise overlapping of p orbitals. P orbitals I'm drawing in yellow. So if this is the p orbital, it will have 2 lobes, one above and one below. what will happen is that these will form a bond in this manner. And one above and one below, this forms one complete pi bond. Over here, we have hydrogen, 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 and hydrogen. They have one s orbital, so that is spherical. Now, to simplify this diagram, we could also draw it as, we could draw the pi bonds as overlapping bonds. This is one pi bond. And now this is shown as a lobe shape. This, along with this, is one pi bond. A more simplified diagram could be and we can show the pi bond in this way. So this was SP2 hybridization, and this is the simplified structure for C2H4, where the carbon has 3 SP2 hybrids and 1 2p orbital. Next is the SP hybridization. Over here, we'll take the example of C2H2, that is ethine, that is an alkyne. It has a triple bond between the carbon atoms. Now over here, we've done this twice. So the excited state, I'm writing directly. Carbon's excited state is in this case, one s and one p orbital combine together to form the sp hybrid. So these two will combine together. So now carbon's configuration will be 1s2, and then there are two sp orbitals and then two p orbitals. So this is 1s, this is sp, and this is 2p. So sp is an intermediate energy level between 2s and 2p. Now the two sp hybrids will form sigma bonds, while the 2p, while the two 2p orbitals will form pi bonds. So again, taking two carbon atoms and the sp hybrids I'm drawing in red. Then this is hydrogen. Now for the pi bonds, I'm using yellow. So this is the first pi bond. And then in black, I'm drawing the second pi bond. So to simplify this drawing, we have carbon and carbon. The three red lines are the sigma bonds. Actually, what happens is that in case of triple bonds, it's a three-dimensional structure. So one pi bond has a lobe above and below, that is in the vertical plane, and the second pi bond has the lobes in the horizontal plane, that is one in front of the molecule and one behind the molecule. This is the simplified structure in 2 dimensions. Next is electronegativity. Electronegativity is the ability of an atom to attract bonding pair of electrons towards itself. The values of electronegativity, you have to remember, we will be given in the data booklet, and they have been determined by the Pauling scale. These are the values given. Now, for example, if we have HCl, in HCl, we'll first see the electronegativity values. For hydrogen, it's 2.1, and for chlorine, it is 3.0. So 2.1 and 3.0, we find the difference. So chlorine is more electronegative. Now, because chlorine is more electronegative, so if this is the bond and these are the two shared electrons, chlorine being more electronegative will pull the two electrons towards itself. So that means that chlorine will have more electrons than its protons, which is why it will have a partial negative charge. The sign of delta is used for partial. So since chlorine is more electronegative, it has attracted the bonding pair towards itself, which is why it has more electrons. So it is partially negative. While hydrogen, it has lost one of the electrons to chlorine, as chlorine has attracted it to itself. So hydrogen has less electrons, so it is partially positive. Now, as these two atoms have opposite charges, so this molecule of HCl is called polar. Now, how to determine if a covalent molecule is polar or if it is non-polar? We'll deal with that in the next video in our topic on intermolecular forces in more detail. Next are the trends in electronegativity. Sorry, I missed one thing. One more thing in electronegativity is the determination of bonding through the values of electronegativity. So if the difference in electronegativity is greater than or equal to 2, then it is an ionic compound. And if the difference in electronegativity is less than 2, then it is a covalent compound. So for example, in NaCl, chlorine has 3.0 value of electronegativity and sodium has 0.9. So the difference is 2.1, which is greater than or equals to 2. So that's why this is ionic. In covalent, for example, H2O. So hydrogen is 2.1, oxygen is 3.5, the difference is 1.4, which is less than 2. So that is why H2O is a covalent molecule. Now the trends of electronegativities. Electronegativity values decrease down the group. This is because as we move down the group, the atomic radius increases, which is why electrons get further away. The valence electrons get further away from the nucleus. So the attraction to the valence electron decreases. So that is why it becomes more difficult for the atom to attract the bonding pairs of electrons toward bonding pair of electron toward itself. That is why down the group electronegativity values decrease. Across the period, electronegativity values increase because across the period, nuclear charge increases. So nucleus to electron attraction is increasing, which is why the atomic radius is decreasing. Again, because the screening electrons are same across the period, the screening electrons are the same, but nuclear charge is increasing. So the nucleus is attracting the electrons more strongly. So that's why atomic radius decreases across the period. So as at the end of the period, there is smaller atomic radius. So at the end of the period, nucleus will attract the bonding pair of electrons more strongly. And that is why the electronegativity values increase across the period. Now, what are the factors affecting electronegativity? They are atomic size, nuclear charge, and screening effect. As we discussed earlier, as atomic size increases, nuclear charge decreases, as was the case down the group. As nuclear charge increases, the electronegativity value increases as the nucleus is attracting the electrons more strongly. While as screening effect increases, electronegativity value decreases because if there are more screening electrons, so there will be less force of attraction between the nucleus and valence electrons. So it will be more difficult for the nucleus to attract the bonding pair toward itself. Next are the bond angles and geometries for covalent molecules. I'll try to explain them in 2 dimensions, but because geometries are actually in 3 dimensions, so it is a bit difficult. So I would recommend you to watch a video, and I'm attaching the link in the description for it. So over there, you'll get the 3D idea of how the molecule is. But in 2D, I'm starting in 2D. So first is when the central atom is surrounded by four things, like it can be surrounded by lone pairs or by bonds. And over here, we will consider a single or a double bond, single, double, or triple bond as a single bond. So what we're taking into consideration over here is the number of lone pairs and the number of bonds and single, double, or triple bonds are considered as one bond. So for our first example, I have CH4, that is methane. Around methane, there are 4 bonds. So there's one hydrogen over here. Now for the other three hydrogens, there is one hydrogen which is in the plane like this. Then one hydrogen is in the front of the plane and one is behind the plane. This is a tetrahedral structure. And over here, the angles are 109.5 degrees. So basically there is one hydrogen above the carbon, one, and the other three are beneath it in a pyramid shape. One is in the plane, one is behind the plane. The dotted line represents behind the plane and the triangular shape represents in front of the plane. And all of these angles are 109.5 degrees. The next example is NH3 in ammonia. Again, there is a central atom surrounded by four things, but the fourth over here is a lone pair. Nitrogen has one lone pair, has 5 electrons. So when it forms 3 bonds, 2 electrons are left forming a lone pair. So over here we'll have one lone pair, then one hydrogen in the plane, one hydrogen in front of the plane, and one hydrogen behind the plane. This shape is called trigonal pyramidal. Angles over here are 107 degrees. Next is H2O. In oxygen, there are 6 electrons, 2 are involved in making bonds. So there are 2 bonds and there are 2 lone pairs. So again, there are 4 things around the oxygen molecule, oxygen atom. There are 2 hydrogen and 2 lone pairs. This is a bent shape. And the angle here is 104.5 degrees. Now the question that arises is that why are these shapes formed? So we have a theory that is called the valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. According to it, electron pairs repel each other, and the repulsion due to lone pairs is greater than the repulsion due to bond pairs. So over here in CH4, each carbon hydrogen bond is repelling the other carbon hydrogen bond, which is why they exist in such a way that there is least repulsion, and that is when a tetrahedral structure is formed and there is a 109.5 degree angle between the carbon and hydrogen bonds. In the second case, in ammonia, we have a lone pair in place of a bond. Now, as I said earlier, the repulsion between the lone pair, the repulsion due to the lone pair is greater than the repulsion due to the bond pair, which is why in ammonia there is more repulsion acting on the bonds, which is why the bonds are bent more inwards and the angle decreases by 2.5 degrees. And over here, the structure is trigonal pyramidal. Next is water. In water, there are two lone pairs. This means that there is even greater repulsion. Now, when there is more repulsion, so the bonds are bent more towards each other and the angle decreases again by 2.5 degrees. But over here, both hydrogen are in the same plane and that is why we have bold lines and not dotted lines or triangular lines. This is the bend shaped and 104.5 degrees angle. Next is when the central atom is surrounded by three pairs. For that, I'll take the example of AlCl3. Now here you might question that aluminum is a metal and chlorine is a non-metal. So how can this be a covalent molecule? The answer is the difference in electronegativities. Aluminum has electronegativity of 1.5 and chlorine has electronegativity of 3. So the difference is 1.5. And we said that if the difference is less than 2, then the molecule is covalent. So that is why AlCl3 will be covalent. Over here, we'll have an aluminum surrounded by 3 chlorine. All the chlorine are in the same plane and the angles are 120 degrees. This structure is called trigonal planar because it's in the same plane. Angles are 120 degrees. However, if we had SO2, sulfur has 6 electrons, 4 are forming bonds with oxygen. So I'll draw the Lewis structure for this. And then there is a lone pair. The last 2 electrons form a lone pair. So that is why when we draw the structure for sulfur, there will be a lone pair over here. Now we did earlier that when a lone pair increases, the angle decreases by 2.5 degrees. So the angle will decrease from 120 to 117.5. Next is when 2 pairs surround the central atom. For example, in BeCl3, again, BeCl2, again, you might say that beryllium is metal and fluorine is a non-metal. So how can this be a covalent molecule? Again, the electronegative difference will be less than 2. That is why it is a covalent molecule. Now over here, there is no lone pair. Beryllium has 2 electrons in its outer shell. So if these 2 bonds are repelling each other, the most stable structure would be when they have a planar or linear structure with 180-degree angle. Next is when the central atom is surrounded by 5 pairs. For that, we'll take the example of PCl5. Now over here, this is a bit complicated. The phosphorus atom has 1 chlorine above it, 1 chlorine below it, and another chlorine in the same plane. Now the other 2 chlorines, one is in front of the plane and one is behind the plane. Now the angle between these 2 and these 2 is 180 degrees, 90 degrees, but the angle between these 2 chlorines and these 2 chlorines and these 2 is 120 degrees. This shape is called trigonal bipyramidal, and angles are 90 degrees and 120 degrees. Next is when the central atom is surrounded by other six pairs, sorry. Then the example is SF6. Sulfur is surrounded by 6 fluorine atoms. So one fluorine will be above it, one will be below it, two will be behind the plane, and two will be in front of the plane. This structure is called octahedral. Angles over here are all 90 degrees. So for example, this angle is 90 degrees. This angle is 90 degrees. This angle is 90 degrees. So once again, I'll go through all of them. The first was when the central atom is surrounded by 4 other pairs. Over here in the first case, there are all 4 bond pairs. So there is equal repulsion by all of them. So the angle is 109.5 degrees and the structure is tetrahedral. Second is when there are 4 pairs around the central atom, but one is a lone pair. In this case, the angle decreases by 2.5 degrees to 107 degrees, and the structure is trigonal bipyramidal. Next is when there are 4 pairs around the central atom, but 2 of those are lone pairs. Then the angle again decreases by 2.5 degrees. The structure becomes bent, and 104.5 degrees is the angle. Next is when the central atom is surrounded by 3 pairs. Over here, the structure is trigonal planar. There are all 3 bonds, and all 3 bonds exist in the same plane, and the angle is 120 degrees. Next, when there are 3 pairs around the atom, but one is a lone pair. Because of the lone pair, the repulsion increases. Angle decreases by 2.5 degrees to 117.5 degrees. Next is when the central atom is surrounded by 2 pairs. Both are bond pairs. So there is equal repulsion and the angle is 180 degrees. The shape is linear. Next, here, all 5 are bond pairs. So the shape will be trigonal bipyramidal with 90 degrees and 120-degree angles. Okay, so over here, in the case where the central atom is surrounded by 5 other pairs, and 4 bond pairs, or 2 lone pairs and 3 bond pairs. But this is the most important of them. And for the more detailed structures, you can watch the videos that I'll be adding in the description. Next is SF6, when the central atom is surrounded by 6 pairs. Over here, all 6 are bond pairs. So the angles are 90 degrees and the structure is octahedral. Now, how to determine determine which geometry and which angle will be present in a molecule. So for example, if we had H2S, now first draw a rough structure for H2S. S will be the central atom. There will be 2 hydrogen atoms. Sulfur has total 6 electrons. 1 electron is over here. 1 is over here. So 4 are left. That means that there will be 2 lone pairs. Now over here, we can see that there are 2 bond pairs and 2 lone pairs. That means that the structure will be bent shaped and the angle will be 104.5 as we did for water. There are two lone pairs and two bond pairs. So 104.5 is the angle and bend shape. If we had, for example, SO2, oh, I did SO2 already. If we have C2H4, that is ethene. A rough diagram for this, there is a double bond between the carbon atoms, and then there are 4 hydrogen atoms. So over here, we'll take any one of the central atom, taking the first carbon. The carbon has 4 electrons, 1, 2, 3, and 4. However, we'll treat the double bond as a single bond. So that means that there are 3 bond pairs. In the case where there are 3 bond pairs, the structure is trigonal planar, as in AlCl3, and the angle is 120 degrees. That is somewhat like this AlCl3. Next example will be N2H4. So nitrogen are the central atoms, and then there are 4 hydrogen. So we'll take any one of the central atom and taking the first nitrogen. For the first nitrogen, nitrogen has 5 electrons in its outermost shell. So 1, 2, 3, 4, 5. There is a bond pair. There is a lone pair over here and 3 bond pairs. This is the case when the angle is 107 degrees and the shape is trigonal pyramidal. That is somewhat like ammonia, this kind of shape. Next example, for example, if we have SO3 2-. So we'll draw a rough structure for this. Sulfur will be the central atom. There are 3 oxygen atoms. So sulfur has 6 electrons in its outermost shell. Over here, each oxygen has 6 electrons in the outermost shell. However, because the charge is 2-, so there will be 1 extra electron in each oxygen. So this will be the shape. Now for sulfur, it has 3 bond pairs because we'll treat double bond as single bond. So there are 3 bond pairs and there is 1 lone pair, that is 4 pairs around the atom. And because there is 1 lone pair, so the angle will be 107 degrees and the shape will be trigonal pyramidal, just like ammonia. So that is how we determine the angle. I'll take one more example. For example, if we have C2H2, that is ethane, which we did in SP hybridization. So structure, there is a triple bond between the carbon atoms, and then there is a hydrogen atom. Now take any one of the central atoms. I'm taking the first carbon. The first carbon or both carbons have two bond pairs because we're treating the triple bond as a single bond. So if there are two bond pairs, that is the linear geometry with 180-degree angle, as in the case of BeCl2.